Our understanding of physics has broken down, and so far, no one can explain why. In 2019, at a conference at the Kavli Institute for Theoretical Physics, Nobel Prize winner David Gross stood before the audience and said what many had thought but were afraid to voice. He suggested we stop calling what's happening a tension or a problem. He called it a crisis. For physics, that word is like a verdict. This isn't just a minor disagreement over decimal points in an equation or an academic squabble in a journal. A crisis means the very foundation of modern cosmology has cracked. And here's the truly unsettling part. The James Webb Space Telescope, the most expensive scientific instrument ever built, was supposed to either patch up that crack or reveal it fully. Instead, it did neither. Webb's observations didn't confirm our existing understanding of the cosmos. They complicated it. And in some cases, they outright contradicted it. Adam Rees, a Nobel Prize-winning physicist from Johns Hopkins University, puts it more bluntly. The observational data points to a fundamental flaw in our understanding of the universe. This isn't a calibration error. It's not a problem with the instruments. It's a mismatch in how we interpret the cosmos. Simply put, either we're measuring the universe wrong, or we're understanding it wrong. And both possibilities shake the foundations of physics. To figure out what exactly went wrong, we first need to pinpoint the core of the debate. At the heart of modern cosmology lies the Standard Model, a set of equations and assumptions that has successfully described the universe for decades, starting from fractions of a second after the Big Bang. This model predicted how galaxies form, how the cosmic microwave background cools, and how matter spreads across space. It worked flawlessly, for years. And the key parameter in this model is the Hubble constant. Just one number. It measures how fast the universe is expanding right now, at this very moment. How quickly galaxies are drifting apart. How fast space itself is stretching between them. It sounds simple. Measure the speed, plug it into an equation, get the answer. But that number has become the most explosive point in all of physics. Here's the fascinating part. The battle over this number has been raging for 100 years. The debate began back in the 1920s when Edwin Hubble first calculated his constant. His initial estimate was so far off that it led to a baffling conclusion. The universe appeared younger than the Earth. The planet has existed for 4.5 billion years, yet Hubble's calculations suggested the entire cosmos was younger. It's like finding a brick in a wall that's older than the building itself. The math checked out. The result did not. For decades, astronomers waged a fierce battle, splitting into two uncompromising camps. One camp stood firmly behind a Hubble constant of about 50 kilometers per second per megaparsec. The other insisted it was 100. That's a difference of 2 times. Not a small detail, but 2 fundamentally different universes, each with its own age, size, and fate. Conferences turned into battlegrounds. Scientific papers became artillery fire. Each side accused the other of systematic errors, bias, and cherry-picking data to fit preconceived conclusions. Decades passed without a clear winner. Then, by the early 2000s, a truce emerged. New instruments and fresh observation methods narrowed the gap. The scientific community reached a consensus, settling on a Hubble constant near 70 kilometers per second per megaparsec. Almost exactly halfway between the old camps. The war ended. Textbooks were rewritten. Models aligned. Physicists finally exhaled. It seemed that way, but the new data from the James Webb Space Telescope didn't just complicate the picture. It started to systematically dismantle what had been built up over decades. To understand why this hard-won understanding collapsed, we need to look at 2 flawless measurement tools, each pushed to the edge of precision, that suddenly began giving conflicting answers to the same question. The first instrument looks back, all the way back, 380,000 years after the Big Bang. That's when the universe first became transparent. The scorching plasma cooled enough to let light through. That light is still traveling, filling all of space. Quiet, steady, barely noticeable. The cosmic microwave background. The afterglow of everything's birth. The European Space Agency's Planck satellite spent years mapping this radiation with a precision that earlier generations of astronomers could only dream of. Every tiny temperature irregularity, variations as small as 100,000th of a degree, holds clues about the density, composition, and shape of the young universe. It's like a fingerprint left by a newborn on the glass of a maternity ward. From that print, you can reconstruct their growth, weight, even blood type. Planck captured this fingerprint and fed it into the standard cosmological model, a set of equations describing how space evolved from the first microseconds to today. The model takes data from the distant past and projects it into the present. The result? The current expansion rate of the universe clocks in at about 67 kilometers per second per megaparsec. A megaparsec equals 3.26 million light years. Put simply, every patch of space that far away moves away from us at 67 kilometers per second. The farther out, the faster the pace. The number fits perfectly. The theory holds. The math adds up. And here, a mystery emerges. Because the second instrument isn't looking back, it's staring straight ahead. A team called SH0ES, led by Nobel Prize winner Adam Rees, measures the universe's expansion rate in a different way, by directly observing real objects in the modern cosmos. Their approach is known as the cosmic distance ladder, built step by step. The first rung involves Cepheid variables, pulsating stars whose brightness changes rhythmically. The slower the pulse, the brighter the star. By knowing a star's true brightness and comparing it to how bright it appears, they can calculate its distance. It's like a flashlight in the fog. If you know how powerful the bulb is, you can tell how far away it is by how dim it looks. The second rung uses Type 1a supernovae, thermonuclear explosions of white dwarfs. Each explosion releases roughly the same amount of energy, making them perfect cosmic beacons visible across hundreds of millions of light years. Cepheids calibrate nearby galaxies. Supernovae reach the distant ones. Step by step, from stars in our neighborhood to the edge of the observable universe. The team led by Rees measured 73 kilometers per second per megaparsec. Not 67, 73. At first, you might just shrug it off. A difference of 6 units. Big deal. But here's the crucial point. The gap between 67 and 73 is actually 8 to 9%. That's not a rounding error. It's not just noise in the data. Both methods have been refined to such precision that their error margins no longer overlap. Statistically, they don't match. Imagine placing 2 certified thermometers in the same room. One reads 72 degrees Fahrenheit, the other 74. Both claim their accuracy is within a quarter degree. One of them must be wrong. Or maybe they're both right, and something's happening in that room that neither thermometer can explain. The consequences of this discrepancy go far beyond a simple debate over numbers. If the universe is expanding faster than the standard model predicts, that means it's younger, not by just a few million years, but by a whole billion. Instead of being 13.8 billion years old, it's closer to 12.8 billion. A billion years is the span during which single-celled life on Earth evolved into complex multicellular organisms. Erasing that entire stretch from the universe's timeline forces us to rethink when the first galaxies formed, when the very first stars ignited, and how much time dark energy had to accelerate the expansion of space to its current pace. Everything changes: age, size, destiny. And yet, we can't just dismiss either method. The Planck data works flawlessly. The cosmic distance ladder checks out too. One of them has to be wrong. But here's the catch. What if the brightness of those very Cepheid stars, the foundation of the entire distance ladder, is distorted by something old telescopes simply couldn't detect? The difference is 6 units. And what's at stake? A billion years and the very integrity of the physics we trust. The most elegant explanation was right there on the surface. Literally, on the surface of the images themselves. Cepheid variables, those pulsing beacons used to build the cosmic distance ladder, didn't exist in isolation. They lived in dense star fields, nested within the spiral arms of distant galaxies, where thousands of stars overlap like city lights seen from an airplane at night. One leading hypothesis accounted for all the discrepancies by this very crowding. Despite its power, the Hubble Space Telescope might not have been able to separate the light of a Cepheid from its closest neighbors. The consequence? Overestimated brightness, inflated distances, and an exaggerated Hubble constant. It's elegant, it's logical, and it's testable. And this is where the James Webb Space Telescope took center stage. Its infrared cameras peer through cosmic dust, distinguishing individual stars where Hubble only saw blurry smudges. Most cosmologists shared this expectation that Webb would finally clear up the discrepancies, recalibrate the brightness of Cepheid variable stars, and calmly bring the Hubble constant down to the 67 kilometers per second per megaparsec predicted by the standard model. The crisis would close. Physics could breathe easy. This $10 billion rescue mission would achieve its true purpose, sharpening our cosmic picture. Early in 2024, the SHOES team published a paper in the astrophysical journal Letters. They analyzed 1,000 Cepheid stars across 5 galaxies, including the distant galaxy known as NGC 5468. Webb's data was fully processed, cross-checked, and compiled into detailed tables. The result? 73 kilometers per second per megaparsec. It was almost exactly the same result that the Hubble Space Telescope showed. Measurement errors were ruled out with a high degree of confidence. The sharpest infrared eye humanity has ever built looked in the same direction and saw the same thing. Neither star clusters nor dust could explain the discrepancy. Hubble wasn't wrong. You might think that would be the end of the story, but by December of that year, Adam Rees's team pushed further. They used 3 independent ways to calibrate cosmic distances: classical Cepheid variables, carbon stars, and the tip of the red giant branch method, known as the TRGB. 3 completely different cosmic lighthouses, 3 distinct physical processes, and 3 separate sets of potential systematic errors. All 3 pointed the same way. The universe is expanding faster than the model predicts. 3 witnesses who didn't know each other gave identical testimonies. But here's what's fascinating. Not everyone agreed. Wendy Friedman, an astronomer at the University of Chicago who spent decades building her own version of the cosmic distance ladder, approached the problem differently. She deliberately moved away from Cepheid variables as the main tool. Instead, she focused on red giants and stars known as JAGB stars, carbon-rich stars in the late stages of their evolution. These stars are less affected by dust and crowding, which means, at least in theory, they avoid the very systematic errors that the James Webb Telescope had just ruled out. In August of 2024, Friedman presented her analysis of the James Webb data. The results were uncomfortable. Red giants and JAGB stars gave a value between 68 and 70. The Cepheids in the same data hovered around 72. Put it all together and you get roughly 70. Not 67, not 73, right in the middle, neither confirming nor definitively disproving anything. Nobel Prize winner Saul Perlmutter responded with a comment that must have unsettled both sides. If different types of stars in the same data give different values for the Hubble constant, the problem might not lie in comparing those results to the cosmic microwave background. The issue could be rooted within the distance ladder itself, even before its value gets matched against the Planck satellite measurements. Riss fired back sharply. He argued that the Friedman team might have used a non-representative sample of supernovae, systematically biasing their results downward. Friedman disagreed. Here were 2 of the world's leading experts working with the same telescope and the same photons, yet reaching different conclusions. Not because either was incompetent, but because the method itself might harbor an unknown variable they haven't yet learned to control. Here's what that means. The newest telescope, built specifically to settle a debate, didn't settle it. It didn't reveal a mistake. It didn't bring the opposing views together. Instead, it started dismantling long-held assumptions, one after another. And at the very edge of those same infrared images, faint outlines appeared, objects that, according to every calculation, shouldn't even be there. When a building starts cracking at the seams, an engineer faces two choices: tear it down or add a new support. Cosmologists chose the second option. One of the most elegant attempts to rescue the Standard Model from the Hubble tension is the idea of so-called early dark energy. Not the dark energy that's driving the universe's expansion right now, but a different one. A hypothetical form that might have existed for only a few 100,000 years after the Big Bang, sparking a brief but powerful surge of expansion, and then vanished without a trace. Like a burst of adrenaline in a runner at the starting line, a sudden push, a rush forward, and then the body settles back into its normal rhythm. Only this surge didn't last seconds, it stretched over thousands of years. And it didn't happen to a body, it unfolded across the very fabric of space and time. The beauty of this idea lies in its surgical precision. A brief surge like this would tweak predictions based on the cosmic microwave background, nudging them closer to what we actually observe. Specifically, 73 kilometers per second per megaparsec, without breaking a single other successful prediction of the model. Mark Kamionkowski, a cosmologist at Johns Hopkins University and one of the minds behind this concept, describes the early dark energy effect as an unexpected jolt the universe received shortly after its birth. A jolt, and then everything proceeds as planned. Mathematically, it works. Physically, though, it remains unconfirmed. But on paper, it looks almost flawless. And here's where the problem nobody asked for appears. While theorists carefully tweaked equations to patch one hole after another, the James Webb Space Telescope quietly got to work, capturing infrared photons from the very edge of the observable universe. What appeared in those images defied every attempt to fix the gaps. The telescope revealed galaxies in the early universe that shouldn't have been there. Not tiny embryos or faint gas clouds, but massive star systems, some rivaling the Milky Way in size, all visible from a time when the universe was only 500 to 700 million years old. To grasp the scale, the universe is about 13.8 billion years old. 700 million years, that's roughly 5% of that entire span. Put in terms of a human life, it's like finding a grown man with a beard and a diploma in a classroom full of 4-year-olds. The Standard Model predicts that, at that time, only small, faint, infant galaxies should have existed. Early, fragile clouds of gas just beginning to form stars. Instead, we find giants. Mike Boylan-Colchin from the University of Texas at Austin tackled this problem with a quantitative approach. His research revealed that the 6 earliest and most massive galaxy candidates sit right at the absolute edge of what the Standard Model allows. Not just outside the comfort zone, literally on the very brink of what is mathematically possible. And even to reach that brink, the model has to accept something physically absurd. To reach such a mass in so little time, these galaxies had to convert nearly every bit of their available gas into stars. Every hydrogen atom, every helium cloud, all of it had to become star material. No losses, no blowouts, no breaks. Normally, star formation operates at around 10% efficiency. The other 90%? It heats up, gets blown away by supernova explosions, or scatters under stellar winds. This isn't some cosmic laziness, it's physics. Radiation from young, hot stars literally pushes away the surrounding gas, stopping it from collapsing into new stars. So somehow, these early giants sidestepped a fundamental limit. It's like an internal combustion engine suddenly running at 100% efficiency, not losing a drop to friction, heat, or exhaust. That just doesn't happen. Or at least, it shouldn't. And this is the second crack, completely unrelated to the first. The Hubble tension concerns the speed of the universe's expansion. Meanwhile, the puzzle of impossible early galaxies deals with how cosmic structures formed. Two different perspectives, two distinct sets of data, yet both point the same way. Something fundamental in our model needs rethinking. Among these objects at the edges of the early universe, strange, compact points with a reddish glow flickered, too bright for their size, too hot for their age. Their true nature was still waiting to be unraveled. In mid-2024, Catherine Chorowski from the University of Texas identified the culprit. Those crimson compact spots flickering in the James Webb data, dubbed the little red dots, weren't what they seemed. Hidden inside each one was a rapidly growing black hole, voraciously consuming the surrounding gas. Here's where physics starts to play tricks. When matter falls into a black hole, it doesn't just disappear quietly. It speeds up to incredible velocities, heats up intensely, and begins to blaze brightly. This emission from accretion, the process of falling in, mixes with the light from ordinary stars in the same galaxy. The telescope sees only the combined brightness. Algorithms assume, if the brightness is that high, there must be a huge number of stars. And if so, the galaxy's mass must be enormous. But in reality, there were far fewer stars. The black hole simply illuminated the system from within, like a flashlight inside a paper lantern, creating the illusion that the whole lantern is glowing. Once those little red dots were removed from the dataset, the picture started to clear up. The remaining galaxies fit the predictions of the standard model much better. Astrophysicist Stephen Finkelstein even went so far as to publicly declare that the crisis was over. The problem was solved. But it was only half solved. Even after cleaning the data, the number of massive galaxies in the early universe still doubled what the theory predicted. Not 10 times more, as once thought, not 5 times, but twice as many. It's like counting guests at a party, removing those who accidentally wandered in from the street, and still finding twice as many people as the invitations sent. The anomaly shrank, but it didn't vanish. One possible explanation lies in the physics of the early cosmos itself. During its first billion years, the universe was much denser. The gas was hotter, packed closer together, more abundant per unit volume. Under such extreme conditions, stars might have formed more efficiently than the 10% rate we're used to. Not 100%, that would still be physically impossible, but maybe 20 or 30%. That alone could explain the twofold difference. The hypothesis was elegant, logical. If that had been the end of it, cosmology could have breathed easy. But in early 2025, the James Webb Space Telescope sent back new images. And in those images, the problem wasn't with mass anymore. It was with shape. The telescope spotted a massive spiral galaxy, nicknamed the Great Wheel, that existed within the first 2 billion years of the universe. 2 billion years is infancy on a cosmic scale. Yet, a spiral structure signals maturity. To form those neat, winding arms, a galaxy needs slow, steady, and orderly growth. Billions of years without major collisions, without chaotic mergers with neighbors. It's like finding a toddler in a nursery holding a graduate degree, not just a big kid, but one with a complex, fully formed life story. The young universe was anything but calm. Every model tells the same story. Back then, galaxies formed through chaotic collisions, mergers, and gravitational mayhem. And a study of 250 galaxies from that era confirmed it. Most of them were clumpy, shapeless, and chaotic, just as expected. But then there was the Great Wheel, a neatly ordered spiral standing out amidst the chaos. Both types existed at the same time, under the same conditions. Models can't explain how that happened. Then came another surprise. A study from late 2025, led by Alvaro Pozo, found that many young galaxies had elongated, cigar-shaped forms. Not disks, not spheres. These stretched-out structures looked more like cucumbers, if you want a simple comparison. The technical term? Prolate shapes. This is where the investigation takes a whole new turn, because the shape of a galaxy isn't just about looks. It reveals the kind of cradle it was born in. And for galaxies, that cradle is a halo of dark matter, an invisible framework holding the entire visible universe together. The standard cold dark matter model predicts very specific shapes for these halos, but cigar-shaped galaxies don't fit those predictions. Instead, they line up perfectly with alternative models, so-called warm or wave-like dark matter, where particles behave differently, creating elongated structures instead of spherical ones. Simply put, if the shape of these ancient galaxies is real, and not just an observational glitch, then the problem isn't with the stars. It's not the gas. It's not how efficiently stars form. The problem lies in the very framework itself. Dark matter makes up about 27% of the entire content of the universe. It doesn't shine, absorb light, or interact with electromagnetic radiation. Yet, it dictates where galaxies form, how they grow, and what shapes they take. Change the properties of dark matter, and you change almost every prediction in cosmology. Every model, every calculation of large-scale structure, every forecast of the universe's evolution. Here's what happened. We started with a question about mass. Galaxies seemed too heavy, too early. We partly explained it as an optical illusion caused by black holes, but behind the mass, we found shape. And behind the shape lies a fundamental question about the nature of the invisible substance holding the entire structure together. We tried patching a crack in the wall, only to discover the crack runs through the foundation. And that matter's distribution across the universe, its clumpiness, its texture, might be nothing like what we thought. Despite the cracks in its foundation, the odd shapes of ancient galaxies, and a stubborn mismatch between two key numbers that refuses to go away, the standard cosmological model keeps working. And not just working. It describes the cosmic microwave background, the thermal glow left over from when the universe was just 380,000 years old, with chilling accuracy. It accurately predicts the ratio of hydrogen, helium, and lithium formed in the first minutes after the Big Bang. It explains the large-scale structure of the cosmos, the vast web of filaments and voids where clusters of galaxies gather at the nodes. A model that handles such an impressive list of tasks can't simply be wrong. But here's the catch. It can't explain the nature of 95% of what the universe actually contains. Dark matter makes up about 27% of the universe. Dark energy accounts for roughly 68%. The model treats them like parameters. It uses them. It depends on them. But what they really are, nobody knows. It's like a perfectly working recipe with two main ingredients listed only as substance X and substance Y. And now, something new joins this long-standing mystery. Beyond the Hubble tension, that is, the mismatch in the universe's expansion rate, there's another lesser-known anomaly. It involves what scientists call the clumpiness of the universe. Physicists measure this with a parameter known as S8, which describes how unevenly matter spreads across space. The standard model predicts a certain level of this unevenness, but observations reveal the real universe is a bit smoother. Matter is spread out more evenly than the calculations suggest. This difference isn't dramatic, yet it persists, and it refuses to disappear. Adam Rees, the Nobel Prize winner whose team measured the Hubble constant using Cepheid variables and supernovae, called this tension the younger sibling of the main crisis. If both problems are real, if the rate of expansion and the distribution of matter both clash with predictions, then we're not looking at two separate cracks. These are symptoms of a deeper systemic failure. And here's a rule worth remembering, not just for cosmology. One anomaly is a measurement error. Two anomalies pointing in the same direction, that's a signal. That's why the next decade will be a turning point. The Nancy Grace Roman Space Telescope, a NASA mission, and the European Euclid spacecraft are already operational or on the verge of launching. Both are specifically designed to study dark energy and the large-scale geometry of the universe. The Gaia telescope will calibrate distances to Cepheid variable stars with geometric precision using parallax with no intermediate steps. This will eliminate another potential source of error in the cosmic distance ladder. Meanwhile, the ground-based Atacama Cosmology Telescope has already produced a new map of the cosmic microwave background. This map nudged the estimate of the Hubble constant slightly higher, bringing it closer to the value derived from supernova observations. But not enough. The gap has narrowed, but it hasn't closed. The verdict isn't in yet, but the tools to reach it are already here. This is where we need to pause and take a broader look. Because cosmology has faced this kind of crisis before, back in the 1990s, physicists hit a paradox that felt impossible to solve. Measurements suggested the universe was younger than its oldest stars. They estimated the cosmos to be 10 to 12 billion years old, while some globular clusters clocked in at 13 to 14 billion. The child turned out older than the parent. The models didn't add up. It seemed like something fundamental was broken. If that crisis hadn't happened, if the numbers had lined up neatly, two teams of astrophysicists wouldn't have felt the urgent need to recheck everything from scratch. The discovery of the universe's accelerated expansion might have been delayed by years, but the crisis did happen, and it pushed scientists to observe distant supernovae, revealing a stunning truth. The universe's expansion isn't slowing down, it's speeding up. Behind that acceleration lay something no one had suspected: dark energy. The answer didn't come from where anyone expected. It came from a place no one was looking. That crisis didn't bury cosmology. It gave it a new continent to explore. The invisible framework holding galaxies together might be completely different from what we thought. The rate at which the universe is expanding could demand new physics to explain it. How matter spreads out may hint at forces no textbook has ever covered. Right now, telescopes orbiting Earth and stationed in the deserts of Chile gather photons carrying these answers. The data is already streaming in. And once scientists process it, whether in a year, 5 years, or 10, the cosmic map will change. Not because the old one was wrong, but because it was incomplete. Like any map drawn before explorers sailed beyond the horizon.